In Chapter 5, we're going to be taking a closer look at stereochemistry at tetrahedral centers. Our enzyme in this slide is glycogen synthase, and this catalyzes the conversion of glucose, which is the sugar that we've consumed, into glycogen for energy storage. So glucose is also a part of carbohydrates that we eat in breads and pastas and potatoes, and when our body doesn't use that, that gets converted into glycogen, which is stored in our tissues. So some objects don't have a plane of symmetry. If we think about a right-hand glove, that is very different from a left-hand glove, and this property in us is commonly referred to as handedness, and in molecules we also have handedness. So organic molecules, including many drugs, have a handedness that results from different substitution patterns on a particular sp3 hybridized carbon or multiple carbons. So handedness is very important in organic chemistry and also in biochemistry. This makes specific interactions between enzymes and substrates possible. And we'll see later that some drugs fit in certain pockets and other ones don't, and that's very much related to their stereochemistry. Molecules that have one or more carbon and have a non-superimposable mirror image are referred to as enantiomers. The carbon atoms where they differ are stereocenters or chirality centers. In order to have a chiral center, we need to have an sp3 carbon or a tetrahedral carbon that only has single bonds, so no double bond carbons. And we need 4 different groups or atoms attached. So this first example here, we have a CH3 and an X. So there's 3 H's here. This one does not have a chiral center. If we have an X and a Y and 2 H's, this also does not have a chiral center. So I'm just going to put no here. And on this last one, we have an H, an X, a Y, and a Z. There's 4 different atoms. I have an sp3 carbon, so this does have a chiral center. So this has a chiral center, and then we have the enantiomer of that, which is the mirror image, and you can see that in the reflection, and it's non-superimposable. So we can draw them flat. We have a C with the CH3, CO2H, H, and an OH, so this one is chiral. And that can be abbreviated with these X, Y, Z groups here. And so we have our 3 different groups. Lactic acid has a chiral carbon right there, and we can see the mirror image of it drawn. The CO2H groups mirror each other. The CH3 group mirrors each other, as does the OH. So that's the plus lactic acid, and we also have the minus lactic acid. And if we rotate those things around and try to match them up and stack them on top of each other, they don't stack. So these do not stack. We can get a couple of things to stack up and match up, but not all of the groups will match, so it's going to be mismatched. And that makes it an enantiomer, and these cannot be superimposed no matter how they are rotated. If we look at a couple of natural examples of enantiomers, we have a structure of carvone, which has that 6-membered ring there. There's ketones coming off of those. We have R-carvone, which smells and is part of the flavoring in mint. The R enantiomer of 1 smells like mint, and then the S compound, which is the enantiomer, you can see that mirror image there, is responsible for the flavoring in rye. So we have those caraway seeds that contribute to the rye flavoring. So those are 2 very different flavors, and the only difference between them is that they are stereoisomers of each other. We also have R-thalidomide and S-thalidomide, and thalidomide was used in the 1950s for pregnant women to treat morning sickness. Infants were born with deformed limbs, and only about 40% of them survived. The S enantiomer was used as the sedative, which helped women with morning sickness, and the R is the teratogen. And here's the chiral center right here. So even though S was used as the sedative, those can racemize in solution. So that means the S can turn into the R. So this was no longer used as treatment for pregnant women for morning sickness. So a chiral molecule is one that has handedness, or a stereocenter, and it's not superimposable. A plane of symmetry in a molecule is going to split the entire molecule into two pieces that are exact mirror images. Not all molecules will have a plane of symmetry. So you can draw a plane of symmetry down the front of your body. A molecule that is achiral can have a plane of symmetry, and one half is going to mirror the other half. So if we look at some examples here, we have the Erlenmeyer flask. I can draw, which is already kind of drawn there, this plane of symmetry. One half of the flask is shaded, which is the mirror image half, and there's the other one. And if they mirror each other, then this is going to be achiral. A spoon is the same thing. There's this plane of symmetry down here. One half mirrors the other. This is achiral. If I draw a plane of symmetry down this hand, one half does not mirror the other half. So this is chiral. Just like when we refer to chirality, this is referring to its handedness. So we think of our hand as an example of something that's chiral. And with this barbershop pole, one half does not mirror the other because of those designs. So this is going to be chiral as well. And then if we look at molecules, and I tried to draw a plane of symmetry down here, one half does not mirror the other. So these are also chiral. And one of the qualities of something like this is that if we have a drug with a specific stereochemistry and it has this chirality, it's going to fit into these active binding sites in enzymes. For our drugs to work, they have to fit into certain pockets. And if you have the triangle, the square, and the sphere that fit into these certain shapes, we take the mirror image or the enantiomer of that. So this one's the enantiomer. We can rotate it around, but they're not going to fit the same way. So this is often the goal of drug design, is to be able to make a drug that fits perfectly in the pocket. If we cut these molecules in half and draw a line down the center, we can see if these are chiral or achiral. And these can mirror each other. So this one is achiral. And also if we look at the four groups attached to this carbon, that one has two H's, which makes it achiral and not a chiral center. So this is propanoic acid. Now if I cut this one in half, I have an H versus an OH. Those are different groups, as is the CH3 and the CO2H. So there's no symmetry plane here. This one is chiral. And then a chirality center, again, just a reminder, we need to have a tetrahedral carbon, or sp3 carbon, and then four different groups. So on this carbon with the asterisk, I have a bromine, a hydrogen, a pentyl group, and a butyl group. So since the pink side has 4 carbons, that is going to be different than the side that has 5 carbons, which makes it chiral. In cyclic compounds, we do the same kind of exercise, but we have to keep going around the ring to determine if a center is chiral or not. If I look at this first example with the CH3 group at 1, I'm looking at this carbon, there's a hydrogen and a CH3, and then I go to the next carbon. So then I go to CH2, CH2. If those are the same, you keep going around the ring. So 3 and 5 are the same, and 4 is literally the same. So this one is achiral because it's the same all the way around the ring. If I look at the next example where there's the asterisk here, I have a CH3 and an H, so those two are different. I go to the next carbon, I have a CH2 versus a C double bonded to an O. That one is different, so this one is chiral. And then if I look at the cyclopentane with the OH, I have an OH, there's an H here. The CH2s are the same, and the CH2s are the same, so this one is achiral. If I start with the Cl, there's an H here, so that's different. These two CH2s are the same. And then I go to the next group. They are different because I have a CH2 versus a Br, so this is a chiral center. And then the Br can also be a chiral center because we have an H here. There's CH2, CH2, and then a CH2 to Cl. So this one has 2 chiral centers. This methyl group here is a chiral center. This one is a chiral center, and this one is. this is a chiral center, and this is a chiral center. So in these molecules, we have two chiral centers. We can look at their overall chirality. This one is chiral. I can't draw a plane of symmetry down it where it's the same, and this is chiral. So this one has chiral centers. But overall, this is achiral, because I can draw a mirror plane where one half matches the other. So you can have chiral centers, but still have the molecule be achiral. So here we're going to identify all the chiral centers. We're going to look to see that we have sp3 carbons in 4 different groups. In this first one, I have an OH. Since that's the only thing on the ring, this one has none, and this one overall is achiral. This OH here has an H, a CH2, and the C to the OH, so that's a chiral center. Same with this one. So this one has 2 chiral centers. I can draw a mirror plane here. That's achiral. On this next one, I have the first methyl group. There's an H here. I have 2 CH3 groups here. So even though it's drawn as a wedge, that doesn't mean that it's going to be a chiral center, because those are both CH3s. So that first one is not a chiral center. This one is. We have a C to a CH3, CH2, CH3, and then a C to the 2 groups here. So those are different. This is also a chiral center, and this one is chiral. I cannot draw a mirror plane down there. Okay, this right here, that is a chiral center. This is a chiral center. And sp2 carbons cannot be chiral, but overall this molecule is chiral. So aside from just determining whether or not something is chiral, we can actually sequence the atoms and give them a specific stereochemistry. So this uses the Kane, Ingold, and Prelog systems. So we're going to look at the 4 groups on the chiral carbon and then rank them according to their atomic number. And the atomic number is what we get from the periodic table. Elements with high atom numbers have a higher ranking, and the low ones have low ranking. If there's a tie in a molecule where there's atoms, you go to the next atom until there's a difference, just like we did with the rings. So if I had a C versus a C next to a CH3, this is the higher ranking one. If I'm looking at an OH, an O, and an O where it's tied, I go to the next atom, which is H versus the CH3. This one is the higher one here. If I have a C and a C, this one has 2 C's, this one has 1. This is the higher ranking here. And then for a C to N versus a C to Cl, chlorine has the higher ranking than nitrogen. So those numbers that we saw up above come from the periodic table. If you have multiple bonded atoms like double or triple bonds, that's the same thing as them being bonded to the same number of single bonds. So a C double bond O is the same as C to 2 O's. And then a C double bond C is the same as being bonded to 2 C's. So once you figure out the sequence, we're going to arrange the molecules in space so the lowest priority group is facing away from you. We count the priorities 1, 2, 3 to determine if it's clockwise or counterclockwise. When we draw the circle, if it's clockwise, it's going to get an R designation. If it's counterclockwise, it gets an S designation. So let's say I've already ranked these molecules. Well, the 4 group needs to be behind. All right, so that's got to be in the dashed position. And then I draw my circle following the numbers 1, 2, 3. If it's clockwise, this is R. All right, in the next example, my 4 is not in the backwards position. So if 4 is wedged, we're going to determine it as normal and then take the opposite. Okay, so I'm going to draw my circle here, 1, 2, 3. So that would make this an S because it's counterclockwise, but because of the 4, this is going to become an R. Right, and that's because the 4 is wedged and we need it to be dashed. So if I look at some examples here, I find my chiral carbon, which is the carbon right here, it's sp3. It has 4 different groups attached. And then I'm going to rank the priorities. Bromine has the highest number, so this is 1. Chlorine is next at 2. Carbon, CH3 is 3. And then H is 4. And that one is dashed and going away from us, so I can just draw my circle here. This one is going counterclockwise, so this one is S. If I look at the next example, I have a CH3, a C double bond to a C, O, and then another C chain here. This is the chiral carbon. The highest one here is O. The next one is not CH3. That one is actually 4. It does not need to be hydrogen all the time. It just has to be the smallest group. And if I look at C versus the C, those are the same. But remember, if it's a C double bonded to a C, that's the same thing as being bonded to 2 C's. So this is 2. This one is 3. So I draw my circle here. This one is going, so it's going clockwise, so it should be R. But because the 4 is wedged, this one will be S. So we're going to look at some problems here. Which of these in the following sets ranks higher? We have H versus Br. Br has a higher number on the periodic table. So that would be bromine. For CH2OH versus CH3, I have a C with 3 H's versus the C, 2 and O. That one is higher. And then if we rank these groups, H is 4. I have an OH, a C, and then a C to O. This one will be 1. The C to O will be 2. C to C is 3. All right, then we have a couple different ones here. I have a C, C, O, C. This is 1. A CO2 to CH3 will be 2. Next will be CO2 to H, and then the CH2OH. And if you wanted to draw those out, that's the CO2H, CO2CH3, OH. So this we said was 1 because of the O is first, 2, 3, and then 4. So even though the OH looks like it's the smallest one, we go to that first atom of attachment to determine the priority. So we've talked about enantiomers, which are stereoisomers that are mirror images of each other. We also have a category of stereoisomers that are called diastereomers. Molecules with 1 chiral center have 2 stereoisomers possible. Molecules with n chiral centers have up to 2 to the n stereoisomers. So if you had 3, it would be 2 to the 3 possible, or 8 stereoisomers if you have that many chiral centers. So I mentioned a different stereoisomer, and that one's going to be a diastereomer. These are stereoisomers that are not mirror images. And in order to have a diastereomer, you must have at least 2 chiral centers. If I look at this first set of compounds, I have the Br and the Cl. In that second compound, if I call this A and B, if I draw this here, are mirror images of each other. So these are enantiomers. C, if I call this C, is also the enantiomer of A. So these are enantiomers. These are also enantiomers. If I took B and flipped it over like a pancake, I get C. So these are the same. D and E are enantiomers of each other, because I can draw the mirror image in that plane of symmetry down there. But the relationship of C to D, the BRs match up, the CLs don't. These are the diastereomers. So another set of diastereomers would be A and D, A and E. B and D are diastereomers, as are B and E. And since B is the same as C, we could replace C, that list as well. All right, we have a practice problem here. One of the molecules below is D-erythrose 4-phosphate, which is an intermediate in the Calvin photosynthetic cycle that plants use to make CO2 into carbohydrates. If D-erythrose 4-phosphate has R stereochemistry at both chirality centers, which structures is it? Okay, so we got to figure out which one is R on both. So if I look at A, I'm going to rank this one here. So there's an H that's not drawn, which is back. This is 1. I have a C to 2 O's, or a C to a O. This will be 2. This one is 3. If I draw my circle, that makes this one R. And then now I have to do the second stereocenter because it has to have R at both chirality centers. There's a hydrogen here that is forward. So that's going to be my 4. I'm going to do it normal and then switch it. So this is 1 will be that one. I have a C to an O, or a C to an O with a C to the carbonyl, and then a C to an O. So this is going to be carbon 2. Gets kind of messy here. This will be 3. So if I draw my circle here, it's going counterclockwise, which would make it an S, but because that 4 is wedged, this one is R. A is the structure of that one, so I'll put A there. That one is D-erythrose 4-phosphate. And then now we need to find diastereomers of erythro 4-phosphate. So in A, I have the OH on the second carbon wedged. This one is dashed. So as long as it's not the mirror image, it's going to be a diastereomer. So these are both dashed. This is a diastereomer of A. This one is dashed here and wedged here. This is the mirror image. So this one is actually the enantiomer of A. And then D is not the enantiomer, so this one is the diastereomer. Sometimes we have what is called a meso compound, and these have chiral centers and a mirror plane within the molecule. If you have a meso compound possible, it's one less stereoisomer possible. So if you had 2 chiral centers, it would be 2 to the 2. You would normally have 4, so we said that it was up to 4. If you have a meso compound, then you only have 3 possible. So in this structure with the BRs here, you can draw a plane of symmetry. I have 2 chiral centers. If I draw this plane of symmetry here, the lower half mirrors the upper half, so this one is meso. But if I have a BR that's dashed and one that's wedged, I draw the mirror plane. This half does not mirror the other half, so this one, even though there's 2 chiral centers, this one is not meso. Now chlorine and the OH here, this half does not mirror the other one. This one is not meso, but it is chiral. This one is also chiral. This one is achiral because of the mirror plane. This here, one half mirrors the other. This is meso and achiral. And in this one, it kind of looks like it mirrors the half the way that it's drawn, but if I rotated the second carbon so that the chlorines match up, so I'm going to rotate the bond here. The chlorine would become dashed. So this one is not meso, and it's chiral. An isomer has the same formula. If we have a constitutional isomer, they're connected different. Stereoisomers are connected the same, but they're different in 3D space. Within stereoisomers, we have 2 types. There's enantiomers, which are mirror images of each other, and the diastereomers, which are non-mirror images. And sometimes we have configurational diastereomers or the cis-trans diastereomers. A constitutional isomer, same formula, different connectivity. So we have different carbon skeletons, where we have 2-methylpropane versus butane. We can have different functional groups, alcohol versus an ether, or we can have different position of the functional group. So below are 2 different amines. One of them is an isopropylamine, and the other one is a propylamine. So we've just shifted where the amine group goes. A stereoisomer has the same formula, same connectivity, but it differs in 3D space. And we have enantiomers, which are the non-superimposable mirror images, or we can have diastereomers, which are the non-superimposable stereoisomers. So there's R and then S on the lactic acid, and here we have 2R, 3R, 2R, 3S. So they're not mirror images of each other. So what kind of isomers are the following pairs? So that top one, they don't look anything like each other, at least in terms of stereoisomers, but we should count up the formulas and see if they are the same. So I have 1, 3. So this is C6H11, Cl. This is C6 from the ring, 2, 4, 6, 8, 10, 11, Cl. They have the same formula, connected different, so these ones are constitutional. And in this one, I have a 2,3 dibromopentane, 2,3 dibromopentane. In the first one, they're both wedged. In the second, they are wedged and dashed. So they're not mirror images of each other. They're connected the same, so these ones are diastereomers. And we have chirality that exists in nature. One of them is limonene, the positive enantiomer, and the positive and the negative, which we won't get into trying to decipher those, but that's how it rotates light. But the positive enantiomer is the oil that contributes to the odor of oranges and lemons, and the negative enantiomer is what we find in the odor of pine trees. We also have chiral medications. So fluoxetine is an antidepressant, also marketed as Prozac, and it's an effective one as its racemic mixture. The R and the S mixture is good for antidepressant properties. If we have just the S enantiomer, that one actually prevents migraines. Your receptive sites for antidepressants can receive either of the enantiomers, as is shown in the hand there, but if you wanted to prevent migraines, you need specifically the S one. We also have other chiral drugs that come from plants or bacteria. These are usually chiral and often in nature can be found as a single enantiomer. Only 33% of them are made in labs because it's very difficult to make chirality centers in the lab specifically and to actually separate them and get them on their own. So penicillin 5 has a 2S, 5R, 6R configuration. There's a lot of stereocenters that need to be made specifically in order to make penicillin 5. So this enantiomer is not something that's available in nature, but it can be made in the lab. However, it has no antibiotic activity. Ibuprofen is an anti-inflammatory that is sold as an AB mixture, or it's racemic. So racemic just means it has the mixture of the two. We can see the active anti-inflammatory agent is A, and B is inactive, but it can slowly convert to A. So as long as there's no detrimental qualities associated with the racemic mixture, they can sell them as both. It's especially helpful that B can convert into A. Naproxen is another anti-inflammatory where A is active. However, with this one, the enantiomer B is a liver toxin, so that one is sold only as A.